So it's really beautiful to look, but there is a lot of physics happening here. There is some recombination of electrons and atomic transitions. And this makes the technique very useful. So here you see in rocks, in metals, in water, and even in air. It's all a matter of how much energy you are putting into this. So in addition to, so this technique is called laser-induced breakdown spectroscopy, and as I said, is the focus of most of the presentations you will see here today. So it's a complex physics, but relatively simple to set up. You just need a relatively powerful laser, focus, pulsed laser, and then you need to look with very high resolution to this light, and some atomic lines will start to appear that allow you to identify the elements that are in the material that you are ablating. So this is very interesting and very powerful because in principle you could shoot the laser either from a telescope, from a distance, or either in a microscope. So suddenly you have a technique with a potential to give you insight on the composition of the material, to make maps, to see from a distance, and you will see during these days that you can go to Mars, you can go to the deep ocean, you can look at works of art. So it's quite amazing what this technique can do, but not all is easy. So LIBS has a lot of challenges. As I said, it's a very complex physics, and here you see two spectra. On the right, you have copper, very simple and very easy to identify the emission lines. But on the left, I think you have maybe steel sample, so with iron, with thousands of lines overlapping. So in this case, even the identification is sometimes not straightforward because you have a lot of mix of the lines. And then all this is in interplay between the laser parameters, the properties of the material. So this makes it very hard and to have a stable and reliable signal. So quantification, if possible, is often very, very faulty, and a bit unreliable, including in many commercial products. Commercial products, yes, because so in the last 2 decades, lasers have become from the size of a truck to a size of a small mobile phone. So you have very, very compact lasers and spectrometers. So you can make very small equipments. There are on the market some of these that you can take a look to what kind of metal you are looking. So they found some niche markets, and where they are working, they are effective. You have also large industrial equipments that can operate in conveyor belts to look at very specific problems. But the thing is, so the project inSITE is on the scope of raw materials and mining operations. We are talking about rocks, we are talking about very complex materials. And for this particular contest, there's not yet in the market a product that can go and really help the geologists and the mine engineers in the operation field. But can LIBS go to such harsh environments? Yes, it can. And here you see the two maybe most extreme examples. On the left, you have operation at 4 kilometers depth in the ocean. So the laser is looking at the rock and shooting and trying to understand what is there, because as you probably know, in these times we are already looking to the bottom of the ocean to some mineral deposits, because we have a lack of these materials for many applications. And on the right, maybe you follow recently the landing in Mars of both the American and the Chinese systems, the rovers that are there. Actually, I think today we have at least three LIBS systems in Mars. So that they are looking at the rocks from this. I think they can shoot even from 7 meters distance, and you will hear Slavka and Dr. Amy talking about this in these 2 days. So quite exciting. So quite extreme environments. So if LIBS can go to these environments, for sure it can work in complex mining environments. The thing is that can we make it useful? This is the question. So now I will go a bit back and to frame how we came to this project. So we go a bit back in the history of INESCTEC, and all started with Eduardo and some colleagues having the vision to define a scenario where we could look at the old mines that we have all over Europe, open pit mines that are flooded. They still have very valuable materials because the price of the materials is rising very fast, but it's dangerous, environmentally costly to explore. So what about if we make a robot that goes underwater and by itself start to explore and explore these materials and take them to the surface where they can be properly taken care, and the water is coming back to the tailing deposit. So no harm done, and everybody is happy. So it's a beautiful concept, but very hard to put together because, so you need to know what you are digging, what you are taking off. You need lots of sensors on the machine, on the barge. You need a special robot to go around and give images to tell the others where everything is happening. So this was the fantasy, and this is the reality, so it was made possible. The concept was demonstrated, so the machine was built and it was underwater operating. And it was in this context that we in INESCTEC, in the photonics group, we built a very simple LIBS system just to answer the question, can it be useful in the mining operation fields? And yes, it was. So we could collect some samples from the machine and from the tailing deposits, and we analyzed very near. So it was a very fast analysis, and we get some interesting results. So the concept was totally validated. You see here the barge, the satellite Rover that was taking the images and the data for the sensors to keep everybody in tune. And all this data from these sensors was fused in the virtual reality environment that you are seeing in this video. So this looks like a computer game, but this is reality, augmented reality, because you have the information fused for all these sensors. And if you are the operator working in this, instead of seeing a very dark space underwater and a lot of dust and turbulence and so on, so the sensors information is fused and given a more controlled environment for the operator to work. Of course, the dream is not yet, we didn't do it yet, but the dream is to take this laser and go inside the machine and be there, and instead of having a map just of the amount of material, you know what you are taking. So this is the dream, and this is the dream that takes us to inSITE project, which is, so it is in the scope of this project that this workshop is being organized. So our vision in inSITE is to have a smaller system, powered by more intelligent software, because to address complex signals you need complex software. Have a database of materials to have some reference. I think maybe Slava will address this. In Mars, they have some kind of also patterns to look and to help the system decide what it's looking at. But all this is as a modular philosophy, because we have partners. Salvatore will give some details on the miniaturization and the very compact and modular scheme where you can change the laser, change the spectrometer, and adapt the system to the different mining operations in different kinds. Because each mine is a different problem. This mine will have its particular challenge, geological challenge, and so the thing is that the philosophy is that the system can be tuned to each specification. And of course, the compatibility with robotics and fusing with robotics, because we want the robots to do the dirty work and do it autonomously. And so this is the inSITE dream. So we were lucky to put together this team. As I will don't give a lot of details, because you will hear from each of these a person, an expert person for each of these centers will give you some insight of what they are doing, not only in inSITE project, but also in other activities. But basically, we are taking an industrial partner, the laser system analytics, to take their technology and incorporate the new research that is being made to miniaturize the laser system, add the database and some intelligent software, and give some information that can be useful to the mining operator. So there is also geologist teams working with us to from the beginning give us a perspective of the project, and Goraz will address this problem in tomorrow. Oh no, I think today. Yes, today. So you will hear details about all this. So this is how it started for inSITE. In our own group, we also keep, and we are running parallel projects, because there is a lot of niche applications. In one of those, a project with the geology department in the also University of Porto and INESCTEC, we are looking at the lithium minerals in Portugal. If you are from Portugal and you are watching the news, you know a lot of protests going on, because they are open the mountains, and there is a lot of. So what if you have a tool that can go to the geologists and they can minimize the impact? They can take decisions. Okay, here is not good. You don't need to wait months. You have the information right away. So this is an attractive tool for this business. So this one of the motivations of the project is to explore the LIBS in the lithium minerals. For this, we partner with a Portuguese company with a fiber laser that has a very interesting control of the laser pulse. Maybe José Vadillo or Salvatore will tell a bit about the importance of playing with the temporal dynamics of the pulse and the detection to get the right function for the LIBS. So we are exploring this in the project with the aim to give the companies a good tool for working. So we started the database, and this database, as I probably Fev and Goraz will tell you, is being expanded in the scope of inSITE. So we are building a large database of spectra with analytical information to provide an environment where the LIBS information can be analyzed with a bit more confidence. So the laser that we are testing, it has some interesting possibilities to change the pulse dynamics, and we can either do plasmas underwater, like we see here on the right, and we can also do something that you will see here, which is not a plasma. It looks so it's a very powerful ball of light, because this has to do with how we change the dynamics of the temporal dynamics of the pulse. We are basically melting the rock, so this can be useful for this if you want to melt or drill the first layers of the rock, and then we want to do the plasma on a second layer. So it's just to show the versatility and the challenges that are still being explored. Other important things, so this is what you see here is a mineral from lithium from Portuguese mountains. And usually a geologist has to take this, go to the microscope and use polarizers and look at the mineralogy, because this is a rich, lithium-rich mineral, but it has actually two different minerals. And one of these minerals is very hard to separate and very costly to explore. The other is much easier and much more easy to explore. So if you are a mining engineer and if you are in the mountain and you make a hole and you shoot a laser, if you know which kind of mineral this is, you can, not just how much lithium there is, but which kind of mineral this is, you have very critical information to take a decision to go or not go for this mine, for instance, and this can make a lot of difference in environmental impact and economical impact of the companies. So, and preliminary results show that in some instances you can make a distinction between two different minerals with the same lithium content, the same composition, but they are arranged in a different, the atoms are arranged in the different crystal arrangements, so it's important to distinguish that. It lacks to see how stable this is and if you can replicate these results in the more dynamic environment. The problem is that this LIBS is let's say, a semi-destructive or minimally destructive technique, because it's micrometer size spots of the material that you are ablating, and Salvatore maybe will tell you that he was even allowed to analyze very ancient Renaissance masterpieces with this, so you can see that it can be very delicate. Actually, if you are operated with LASIK to your eyes, you are using a laser plasma to make the operation, so this can be very precise as well, okay? But if you are doing mapping and you are making small holes on your sample, you want to minimize this. So we are also working in some adaptative mapping algorithms. So this is a transition of two different minerals, and you can either use the brute force approach and make a square matrix of analysis points, and this will take more time, more energy, and will destroy more your sample. But you can either take the decision either based on the image and also on the composition of the signal, of the laser lines that you are looking. You can make the decision to use the most of the analysis effort on the transition, because you know the algorithms start to learn that this part is uniform and you don't need to spend so much. So this adaptative mapping can be important to save time and money and be more efficient. So this is some examples of what you can do, but we will see much more during this afternoon and the next afternoon. Just a small teaser also for some research we are doing in INESCTEC. We are considering, can we combine this with LIBS? We don't know. So what we are seeing is that here we have a laser, we focus the laser, not so much energy as in the LIBS, otherwise we will destroy everything. But there is enough power so we can create a force field where you can trap the microparticles. In this case, cells. You can see here some polystyrene particles, some microalgae. So if you make the polarization of the light rotate, you can make the particle rotate as well. And we can fabricate some micro lenses to implement this. So we can play. It's a lot of fun, but can we make something useful? Yes, we can, because this signal, although it's a bit chaotic, the scattering signal of the light coming back from the part being analyzed, if we use a position-sensitive detector, you can also gain insight in the Brownian motion and the combination of Brownian motion with the optical force. And this has unique signatures that you can actually say if this is a cancer cell, if this is a healthy cell, if this is a microplastic, if this is a microalgae. So this is very interesting. So we are already working on this and making real-time classification of the cells. So why not put the LIBS into the equation, and you are scoping the ocean and looking for microplastics, and you analyze or destroy the cancer cells. So just a teaser. You won't be hearing about this in this part on the workshop. So, but I hope with this very brief overview, now I leave the floor to the very, very competent speakers that we were kind enough to accept our invitation. I hope I convince you that LIBS is a very interesting tool that with a strong potential and enormous challenges. These challenges, of course, are opportunities for us researchers and engineers to make new stuff, new research, to investigate. And in the case of inSITE team, we are working to make, so we want this system to be useful for the raw material exploration. And the inSITE team is committed to work to make this goal a reality. So please enjoy the workshop, learn as much as you can, and if you wish, afterwards, you are students, most of you, join us in this adventure. So I'll leave you with some, this is the inSITE links, you are already this, and some pictures of Portugal for you to be motivated to come here presentially. Thank you very much, and I will be here in the next 2 days. I will be your host. Anything you can contact me and the team, so we'll be glad to help. Thank you. Okay, so since I'm the host, I remain for now just in the same place. And so it's my pleasure now to invite Professor José Miguel Vadillo to the floor. So he is an analytical chemist. He's a full professor at Malaga University. He works in the very exciting Malaga Laser Lab. So he will show you some. He has a lot of work, very fundamental work working on the dynamics of the LIBS, analyzing the effects interaction with the materials. His team is also involved with the analysis and simulation of the Mars environment. So please, José Miguel, if you want to.
Okay, thanks very much, everyone. Muito obrigado for the invitation. First of all, let me apologize for my lack of dressing code. My luggage is supposed to be somewhere in between Madrid, Zurich, and Porto. It was lost yesterday, so I got a beautiful suit just to look sharp in front of you, but right now I'm as casual as you can see. So apologize for that. Second thing, before going into the kill, I would beg you to keep the high hopes but low expectations about my talk. I'm not as good as Pedro pretends to picture, but I will try to provide a good overview of what we are doing. Just a basic draft, just to convince most of the students that I'm really happy of being talking in front of you. And my background is biology. So if I'm here talking about laser and laser physics, honestly, any of you, much smarter than what I am, could do whatever you want. I did my PhD in analytical chemistry, of course, and after my BS in biology, and after that, I started playing with lasers in my research group, in my current research group, and I'm here. So let's start with that. I stole the main slide of the project to talk briefly about direct analysis of solid samples, condensed phase samples mainly, although it can be extended to any physical state of matter, using particularly laser-induced plasma-based spectroscopy. I will just focus on optical emission of laser plasma, optical spectroscopy of the laser plasmas, but we do in the lab some other side techniques as Raman and particularly in my case, mass spectrometry of laser plasmas, what we call laser ionization mass spectrometry. Pedro told me yesterday that could be interesting for any of you, probably not skilled in what laser-induced breakdown spectroscopy is, in providing a primer on LIBS, fundamental back to basics on LIBS, and I am happy to do that. So I just provided 4 or 5 slides talking about basics with the aim of a better understanding of what it comes in the next slides. The first thing, if we want to provide a quick run title of what LIBS is, we basically torture our sample with a laser as a source of photons. Depending on the type of laser, depending on the wavelength, depending on the pulse width, depending on the repetition rate, depending on many aspects, the key thing here is that we just use the laser, the photons associated with the output of our laser to excite the sample, excite the material. And in this excitement, we normally heat up the surface, the sample, the bulk, depending on the amount of energy. And in this excitement, normally we end up in a plasma formation. But depending on the amount of energy that we put into the process, we can do many different things. If we move to cooking, that works perfect for laser heating interaction. If you want to grill a piece of meat, you put the grill very high in temperature just to create a crust on the surface. If you want to do a well cook, normally what you do is low temperature during an extended period of time. This basics idea, basically we're talking about the Fick law of heating into conduction into a solid, works for laser. Short pulses, high energy, create a different effect on the sample than a long pulse laser extending over a period of time. And in a very, very simple cartoonish type slide, you will have it here. Normally in LIBS, we use short pulses. We will define what a short pulse means. Normally, we're talking about nanoseconds and below, nanoseconds, picosecond, or femtosecond pulse width, but we'll still have some lasers. For example, Pedro has mentioned fiber lasers or even some microsecond lasers that has a long pulse. And in any case, in both of the cases, what you have, if you could monitor the profile of intensity over time of your laser, in blue, normally the temperature rises to a given amount, delayed a certain space of time, a certain period of time, with respect to the centroid of the maximum of the intensity of the laser profile. That happens when you have a single pulse. Of course, if we increase the repetition rate that you have here on this side, you increase the repetition rate here of, in this case, as a worst case, in the range of kilohertz, the temperature profile over the sample is completely different. In LIBS, normally we operate in this field, in this period. The physics behind is complex. I would say that still unknown. There are too many non-linear effects that we don't really understand properly. The key thing, again, is the decoupling in time between the reaching of the first photons to the sample until we have a laser that grows and we can monitor it. This period of time that occurs can be several hundred picoseconds. During these several hundred picoseconds in time, many different things are happening in the sample. Many different things are happening at an electron scale. Electron-electron recombination, electron-electron heating, electron-photons coupling, many different things. And after this time, the whole sample, the volume affected by the laser, thermalize, and depending on the overall amount of energy, it will build up as a plasma or will just stay as heating, local heating on the sample. Depending on the energy, you have this picture. Sorry, I forgot the reference. It comes from the doctoral thesis of, you know probably him and Renato Zenobi. He did his PhD in Stanford in laser desorption. I did my postdoc there, and in his thesis he was doing a lot of fundamentals of the heating of the sample, and he has this nice picture where it's telling you that at low energy, in the terms of 10 to the 4 watts per square centimeter, we will forget about if this is low or high, but in general it's low. There is a huge period of time until the surface vaporization starts to begin. If you increase the power, if you increase the fluence, if you increase the energy density, the vaporization starts sooner. That's the play that we can do. And in terms of the time scale of the different processes, again, in a very cartoonish way, what you have is that in a period below the very first picoseconds, we will not define strict boundaries on the time scale because there are too many factors that affect that. But in the range of the picosecond, you have the absorption of from the bulk, from the surface, of all the energy that it is contained in the photons, plus the energy that it's added because of different photons, electrons, photon lattice interaction. And after a period of time in between the picosecond, the range of picoseconds and a few nanoseconds, what you have is what we call the breakdown, the melting, the explosion, the phase explosion, and you have what we call a plasma. This plasma starts to expand against the surrounding media, and again, this adds a large diversity for the analysis. If we change the pressure, we change the gas composition, the chemistry between the plasma and the surrounding media changes quite a lot. So the plasma expands for a period of time. In this period is where we normally are monitoring the photons emitted by the plasma. And once the plasma vanishes, the affected region by the laser melted again with a region that has been affected by the process of heating and cooling. The region changes. His composition has a crystallographic structure, and in sometimes you will have what we call a rim, some material that has been deposited in the craters, around the craters, forming a rim. Again, in the time scale, just to fix these ideas, the plasma starts, the laser reaches the sample at, let's say, time 0, and process 5, 6, or 7 that has to do with the plasma expansion starts to be seen in the time scale of several nanoseconds. Again, run title, photons reach the sample, nothing occurs, microscopically speaking, until several hundreds of picoseconds at least occur. We have developed techniques in the lab where we could see all these different surface modifications in this low picoseconds regime, but it's not the moment to do that. Depending on the energy, we can play a bit with what we can do over the sample. First, very simple experiment. We have the same laser, we tweak it in energy, low energy, and if the energy in the center of the laser normally has a Gaussian profile, so in the center where we have 90% of the energy of the laser, if this region, the energy is just above the melting enthalpy of the sample, basically we will just melt the sample, but once the laser is off, nothing will happen. Maybe some slight modifications, but basically there will not be mass transfer. We will not generate a plasma with phase explosion and particles coming out of the affected volume. If we increase a bit, and this a bit can be a few microjoules, as as tiny, as little as this, maybe we have energy enough to exceed the vaporization enthalpy. In this case, this amount of sample, this volume of sample, will have energy enough to switch from condensed phase to gas phase. It will blow up, and we will have a plasma or not, but this material will not be anymore in the crater. It means that once the laser is off, what we will see is a crater with some mass removal. Knowing that we can play with that, now it's very easily to be understood how we can play with our laser to modify, to change what we want to do with our laser. In this, let's say, energy scale, the energy ladder of the processes, if we start with our laser at very, very low fluencies, most of the physical process are affected by the interaction of the photons with the sample, what we call the photoablation regime. In this photoablation regime, basically what we're doing is very basic things. We can decolor the surface. We can maybe generate a small desorption, nothing more than this. Very interesting and very useful. Don't forget that if you want to get rid of this tattoo that reminds you your ex-girlfriend, for example, and you do it by laser removal, you are in this regime. If you go to the dentist to do whitening of your teeth, you are in this regime. If you want to do some surgery of your eye, you are in this regime. But if you crank it up a bit more, the energy of the laser, you start having more energetic processes, and now you will not decolor, you will not desolve anymore, you will start in the thermoablation regime, and in this process you will start by having some thermal ionization, generation of ions by thermal emission. You will have some clear, significant alteration, modification of the surface roughness. By the way, very interested in some optical processes, in some engineering processes, and at the end you will have a vaporization and a plasma formation. And all these things can be done with the same laser just by modifying the energy. So you have a lot of play, a lot of fun if you want to go deal with that. Well, Pedro has shown what a plasma is, so let me introduce it again, just to talk a bit more about that. This is a picture from Enrique Russo at Berkeley lab, national lab. It's in a helium atmosphere, to see it purple. And what you have here, this is the plasma. What you have here is the expansion of the plasma on the surrounded medium. The plasma itself is this thing, and this tiny thing that can be about 2 millimeters in height. What you have there is a whole laboratory at tiny scale. You will have, this plasma contains a huge amount of ions per volume, so the electron density is huge. You will have, the electrons that you have will be in very high states, so the electron temperature is high. You can access levels 2, 3, 4. You can see it in the ionization levels, even higher. You will not have any restriction in the type of samples to generate this plasma. Can be a solid, the general case, can be a liquid, can be a gel, can be an aerosol, can be a gas, can be melted steel. No restrictions at all. You can play with any type of samples. No restriction about the electrical conductivity. No restriction about if the sample is magnetic or not. No restrictions at all about anything. LIBS is absolutely universal in the type of sample. That's one of the virtues of LIBS when it comes to chemical analysis. And a second interesting thing, if you enjoy wasting your time in the lab, is that in this plasma you have any type of chemical species that we know. What I'm meaning with that is that in this letter soup that we have in a laser plasma, in LIBS, we just monitor the photons. But we can do Raman because we have molecules there. We can do mass spec because there are too many ions there. So you have photons, you have molecules, you have fragments, you have isotopes. The only thing that changes is the type of detector. If you have 2, 3, 4 different types of detector, you can do too many things with a single laser plasma. In terms of configuration, there are as many configurations as research labs. Normally, with a few exceptions of some commercial system, it's quite normal that you mount as if you were playing Lego. You mount your laser specifically trying to tailor your particular application, but the general scheme is the general scheme is general. That's absolutely stupid, but you know what I mean. You need a laser. You need a way to guide your laser to your sample. You need your sample. Hold it in any stage or whatever. You need some optics to collect the light to your detection system, and basically that's all. That's the basic. These 4 things is the only thing that you need. You can make it as complex as you want, but basically every single laser setup will have this. So I will, in the next few minutes, I will try to explain some of the experiments that we have in the lab, with the idea of trying to convince you about the beauty of the technique, the work that we are doing, and trying to convince you how flexible, how open, how versatile is the technique. In this moment, I would like to say that I will be more than happy if any of you interrupt me asking wherever you might consider. So I'm absolutely open to answer any question. And of course, during the days that I'm going to be here, I will be really happy to talk to you if the LIBS is creating any interest in you. Okay, that's where I'm coming from. That's our laser. It's called UMA Laser Lab. Well, Laser Lab is obvious. UMA is University of Malaga, so we didn't squeeze our brain looking for the name. And in principle, our lab is completely focused on laser-based, in general, analytical approaches to solve what we call contemporary challenges. The lab, we moved to this facility about 6 years ago, and the lab, basically, it's divided, has a focus on 3 different aspects: understanding some fundamentals of laser ablation in general, or laser matter interaction. Of course, we are into applications, and of course, focus, in the techniques, trying to implement techniques to the lab. To do that, we've been for almost 25 years working on LIBS, so we have quite a significant amount of infrastructure now around LIBS. But in general, we cover all the different types of excitation sources that you need for LIBS in the nanosecond, picosecond, and femtosecond regime. Not going to go into detail for that. In terms of detectors as well, we have systems to monitor with a very fine temporal resolution things that happen. Detectors just to cover broad range of time. Mass spectrometers, spectrometers to perform that allows us to have isotopic resolution by optical spectroscopy, has been recently installed. Mass specs to monitor ions, so on. So the best thing I can do is that I'm obviously inviting any of you to show up in the lab anytime that you want, and the visit there will be the best business card. In brief, what we have are experiments that cover these three types of approaches that basically are the three main approaches in LIBS. The one that you have in the top of the slide is what we call close contact LIBS. It's the general way of doing LIBS, where the sample comes to the lab, you put it on top of an optical table, and your experiment is around the sample. That's close contact. In this close contact, there are subtle differences. You can maybe, for flexibility, maybe the sample is collected through a fiber optic. Sometimes the laser is guided through a fiber optic, but it's relatively confined. The spatial domain is around an optical table. In some cases, you can build, and we will see some examples, you can build some portable experiment where you have the laser, the detector, and everything in a tiny container, a backpack, or something similar, and you could move this portable lab to where the sample is. But in any case, the sample is close to nearby to the experiment. In remote analysis, there are two approaches that we have worked quite a lot. The first one would imply having your laser at a distance from the sample, and in order to excite the sample, what we do is deliver the photons that comes out of the laser through fiber optic to the sample, and in this case, depending on the length of the fiber optic, the analysis distance will be lower or higher, and the same photons that has been generated by the sample will travel back to the experiment using the same fiber optic. We will show you examples on that. In that case, the only limitation is the attenuation of light through the fiber optic. There is depending on the laser wavelength, you can put more or less energy in the fiber, and you can run a distance. In our cases, I will show you, we have some experiments tailored to do underwater analysis. We can go up to 100 meters underwater, but not more, with the lasers that we have and with the wavelength that we use. And the second approach that is very interesting, the ones that we have in Mars right now, is what we call real standoff, where the laser, just by playing a bit with the optics, is focused at a distance without nothing in between. There is just direct eyesight distance, the only thing you need. The laser is focused to the sample, and again, the photons generated by the samples fly back to the detector. In that case, this distance can be, in principle, any. In practice, can be, we have run experiments up to 400 meters. In LIDAR, a technique that many of you know that uses laser fluorescence, can be several kilometers. At the end, it all depends on the amount of energy that you can generate in your sample. As we need a plasma, we need a given threshold. With conventional optics, we can reach about 400, 500 meters. In particular case of Perseverance, the rover now in Mars, this distance is, as you know, in the range of 15 meters. But 400 meters is quite a lot if you think about that, considering that you're analyzing at real time the composition of the sample half a kilometer away. Okay, the lab, because I'm running out of time. This is the lab, basically the disposition. Just to prove, I'm gonna tell you different examples. Office, main lab, where we have I will detail now our thermal vacuum chamber for the Mars experience we are running, the femtosecond LAR, completely isolated from the rest of the lab, and some different spaces. This is a general view of the lab. Well, this is the big chamber, as you can imagine. Any different experiments are in a different optical table. That's the main lab. We have there are 2 or 3 additional rooms for different experiments. Femtosecond lab has a specific room just because of the temperature that we have to keep in the laser. Many things that we can do there. Some very fundamental experiments that has to do with the physics of the laser-matter interaction, but also in this lab, we can do laser ionization mass spectrometry of solid samples. In this particular case, Pedro mentioned about the spatial resolution of LIBS, but let me extend it to laser analysis. We've been able to go down to 5 microns with a femtosecond laser and with removal rates in the range of 1.2, 1.3 nanometers per shot. What is really huge, a big number. The experiments are very flexible. We can run with different vacuum chambers, different laser sources, different spectrometers, a shell, Thorny-Turner. Our configurations are very modular. So from week to week, everything is changes depending on the type of experiment that we are doing in this moment. The femtosecond laser, nothing wrong here. We do a lot of experiments in trapping. Pedro mentioned your experiments on trapping here. We do trapping in air. We've been able to trap successfully particles down to 25 nanometers, single particles. That means absolute detection limits in the range of low attograms. That's a world record in absolute sensitivity in LIBS ever. We trap the laser. We trap the particles with a regular optical trapping with a continuous laser. The particle that is trapped can be analyzed by fluorescence, by different techniques, and once we have it fixed on a specific point, we hit it with a second laser, and we get the LIBS spectra out of it. We have different lithium papers on that, so if you're interested, I can provide you, but it's something that is surprisingly working. Stand-off to remote analysis. We have been building the last 15 years, like 8 different experiments. The 2 that are the most appealing, let's say, are these two puppies at here. The one here is what we call the mid-range. This system has the laser here, it's a double pulse laser with a telescopic arm. The whole system can be moved, so we can point at the laser at any desired point, and we can do with this system LIBS and Raman. Raman is a very complementary technique that provides molecular information about the molecules, not about the atoms, that it was LIBS provides. And the second experiment is what we call the long range. This has been tested up to around 300 meters. In these several projects that we had in the past, working with detection of explosives. And again, it's working, and it allows, again, LIBS and Raman approaches. So don't want to go much into details. Many different applications on that. Melted steel, we've done a lot of things going into factories with the capability, because we can be away of the sample. So even in these extreme environmentals, with these stand-off techniques, it's very easy to provide real-time information. Not going to go into details. 3 minutes, I'm finishing. Underwater subsea experiments. This is the last generation. It's the 3rd generation of experiments that we've done. This is the 3rd one, the most beautiful and compact. One module that includes the electronics, generator, and so on. It's absolutely autonomous. You don't even, if you don't have power cord, you don't need it. And the optical module that includes the laser and all the optics and the detectors. The key thing here is that the laser is delivered through a fiber optics that goes here, 40 meters, 60 meters, 100 meters, depending on the attenuation, of course. And the probe includes the collection optics to bring the photons back to the detector. The only thing that goes undersea is, of course, the diver and this cable. The rest of the modules are in the ship, are in air. Things that we have done, the very, very basic approach was submarine archaeology, monitoring. As you know, we've been fighting with English, French, Italian, Greeks. That's the history of Spain, losing battles. But and we have a huge bunch of ships that are shipwrecks in the coast of Bay, Malaga, and this region. So the archaeologists are interested in monitoring the different pieces that have been there for centuries, and the diver is here with the probe, and you just have to be there, analyzing things, and providing information about the elemental composition of the pieces that you will find here, just as a way to build a catalog of things that are undersea. Portable things, of course, we can do the same thing. I'm going to skip this. Applications, well, patrimonial analysis, of course, plants, steel plants, caves, Carthage caves, and of course, patrimonial studies. In this case, is the Cathedral of Malaga, the main portico of the Cathedral of Malaga. Again, trying to analyze in a very simple way with a portable thing the elemental composition of the surface. Finishing in the last 2 minutes, what we are doing with Mars. We are part of the research team of the Perseverance mission. The head of the lab, Javier Lacerna, is one of the co-IPs, co-principal investigators, and we will be, in this case I will be as well, part of the ExoMars, the one that will be launched in 2024. This is the first spectra, many of you know, of LIBS spectra taken out of Earth. It was done in the Coronation Rock. Since this period, since 2012, many things has happened, and this is the laser, the setup that was installed in the Curiosity rover that is still getting data in Mars, and this is the one installed in the Perseverance. This module includes a Raman laser to do LIBS and Raman, apart from some other techniques. There are 7 analytical techniques in this block. As we're part of the mission, we decided to get some, to bring to the lab some infrastructure that could help to understand the data and provide data that could be commanded to the rover at real time. To do that, we got money to build this 12 meters long, internal diameter is 1.6 meters, that can reach vacuum up to 10 to the minus 5, 6, depending on the pumping that you use. Of course, we can fill it with any gas that we want. We have a solar illuminator, but basically, particularly with the Perseverance, with the Mars 2020, we can mimic the condition of Mars in our lab. We can run temperature cycles, things like that. When it comes to spectroscopy, what we have is building a laser and a LIBS and Raman experiment. We will have the samples at any distance between normally 2 or 3, that is where the calibration target is, the calibration target is in the rover, until 12 meters, that is the maximum distance of the LIBS laser in the Perseverance rover, and we can run experiments, including the acoustic monitorization of the sounds of the laser plasmas, a new instrument that was included in the last minute in the mission. Just to provide you 2 examples, a spectra, black trace, the spectra of hematite, very basic mineral, in Earth, red, the spectra in Mars, under Mars conditions. There is, of course, a decrease in the intensity, a decrease because of the distance, but the amount of peaks, the position of peaks and everything remains the same. So the spectra are of high quality. If we put several samples in front of a laser, we have different spectra, looks like very similar, but if you tweak the arm of and do some chemiometry, you have the possibility of running classification. If you add a second analytical dimension, in this case, the microphone, you can analyze the acoustic spectra from the laser plasmas. This spectra looks very similar, but you can do some post-processing of the data, and you may have differences in the different minerals. Here you have iron-based minerals and some carbonates. And if you combine both data fusion, you may have a thing like that, a perfect classification of minerals. If you have a database and you have done things like that, maybe you can detect unequivocally spectra that you may find. Okay, I've been almost stuck on time, so no conclusions. I'm finishing with that. You have my email here. You have Anna knows me, Pedro knows me. Feel free to contact me anytime. If it's with a beer in front of us, much better. And thanks very much, all of you, for your attention. Muito obrigado.
Thank you, José, for a very inspiring talk, showing us all the possibilities of LIBS. So José is happy to answer questions you might have, so please don't be shy. Some of you or most of you are students, so don't be shy to make
don't be shy. I'm not even wearing a suit, so you shouldn't be shy.
What is the optical trapping configuration that you have used? A counter-propagating waves, a single laser?
In this case, is the simplest configuration that you can imagine. A tiny CW laser, continuous laser. I can't remember the energy, but in the range of 200 milliwatts, something like that. An objective, and that's all. The only thing, as right now, we confine the nanoparticles just for safety reasons on cuvettes.
Okay.
Okay. But we have a third laser, a second laser that performs catapulting of the particles, because if you're working with very tiny particles in these nanometric range, they tend to stack on the bottom of the cuvette. So we hit a laser that is in the same optical axis that the trapping laser. This first laser just hits the particles. We have a cloud of particles, and just in the waist of the trapping laser, we have 1, 2, or 3, whatever particles. They remain there. We've been having particle traps for 8 hours, if I remember properly, there in the same position. And once we have them, the third laser hits the particles to get the LIBS spectra. So the configuration is very simple, surprisingly simple considering the output that you have. Of course, we had the idea. We have been working on that, doing counter-propagating. That's something that we are doing. We are trying to apply. We have the possibility of maybe doing some near-field optics in order to enhance the field, but it's too tricky. We want to keep things flexible. We are now working with a group in the University of Navarra in Spain, combining acoustic levitation with optical trapping, standing waves and optical trapping. So there are many things going on with that, but the configuration, as I told you, is very simple, very simple.
Okay.
600 euros laser, green, works for that. The only thing is that depending on what type of particle you're using, you're talking about cells. In our case, we're working mainly with metals. Plasmons are out there. So the plasmonics, that basically is a wavelength-dependent process, affects the type of particle that you trap, even the geometry of the particle that you trap. But brasses, metals, things like that, we've been doing a bunch of things. Graphene, nanotubes, with a green laser, green DPSS 300 milliwatts laser, works beautifully.
Okay. So you are using metallic nanoparticles, right?
We're mostly working with that.
Okay.
we can do with cells or things like that, because basically you are frying the samples. But with the approach that we have right now, we haven't tried yet.
What is the power of the laser that you use for trapping, and what is the spot size? Do you know?
The spot size, if I remember, is in the range of 15 microns. Okay. Maybe, but I wouldn't like to burn my fingers in that range. With 200 milliwatts, something you can focus it, and the microscope, the objective that we have is a very general microscope from Thor Labs. Yeah. So probably is around another 500 euros, something like that. It's not the most sexy microscope in the world.
Okay, thank you.
No problem. The question is good. The first answer would be the simple pleasure of doing it, what is not very scientific. The second thing is that in atmospheric chemistry, if you're familiar with the literature, there have been many approaches using radio frequency traps, acoustic traps, things like that, because there is a clear interest in the pure physical chemistry understanding of what the aerosols and particles do, of trapping things and follow the different chemical processes that happen there. So what we wanted to do something similar in air because of the flexibility, and just doing LIBS because it's our technique. But of course, we would like to do it in some other approaches. In the practical approach, right now our system is useless. Right now. Right now we are the only group in the world doing single particle analysis by LIBS. So sometimes you just develop the technique, you are running proof of concepts of things, but who knows if someone catch our idea and decided to put it in a different level. But of course there is interest to do that. Probably the main interest will come not in the approach that we use, directly analysis of the samples, but for example combining laser tweezers, putting the laser close to the waist of the trapping laser, and putting these samples where we wanted to analyze it and bring it down to any other place. Maybe combining, as I told you, optical acoustic trapping with that. Maybe a combination of near field of cells or particles in water, trapping them, getting them out of the aquatic environment, and bringing them to air where we can analyze it with our technique. So sky's the limit. But the first thing you need is the technology. The second thing, is that from the fundamental point of view, when you're hitting your laser on top of a sample, your sample is surrounded of a huge volume of sample. So the energy travels in 3 dimensions, and you have what we call matrix effects. When you have a particle that is levitated, it's isolated from anything else. So the type of spectra, the amount of energy you put, and the interactions are completely different than when you analyze the same material in bulk form. So even from the fundamental point of view, still very interesting, this type of approach.
The next speaker is a very old friend, Goraz. You are ready? Yes. Okay, come. Goraz is a geologist from a geological survey from Slovenia. And Goraz is a consultancy in some programs, European Commission also. They work in design and also impact assessment of the mining sites. And they have, I don't know if it is a lobby, but Goraz also like a lot to explore the artificial intelligence and deep learning in data sets. Is it true? Yeah? And today go to present something about this project or more?
A bit general.
Bit general. Okay.
A general picture of all
All
the
right.
story.
Stage is for you.
Yeah, my name is Gora Žibret. I came from Geological Survey of Slovenia. And I would like to present you a bit more of general picture. So I'm geologist, mineral resource geologist and geochemist. And I'm not really an expert on LIBS, but more on mineral resources. And I would like to give you a brief overview of how these LIBS can be used in broader sense. And talking with Anna, so how to tailor this, we decided it's good to present you our vision of the mines of the future. Before we begin, really I would like to show you two pictures. The comparison of road construction like 100 years or 150 years in the past and road construction, tunneling construction today. And the changes are very obvious. Either the number of workers you need there, the casualties, the health and safety, the speed of the construction, and all that kind of stuff. Let's go back to mining. So why do we need mining? Do we have laser here? Does it work? Okay, great. So global demand of raw materials and energy is increasing, and what is even more interesting, that the demand of minerals per capita is increasing, as it is obvious in these two graphs. So the amount of copper per person is increasing, and couple this with increasing number of people it lives on the planet, which live on the Earth, we were quite sure that demand is growing. And variety of resources we need today is also increasing. So today we are using probably for sure the majority of periodic table elements in the periodic table needed for all kinds of electronic devices, clean energy, batteries, etc. Recycling cannot meet the demand. Even if we recycle 100% of all resources, it will still not meet the demand. But what is even worse here, not all of materials are recyclable. Some are very good recyclable, some are not so good recyclable, some even cannot be recycled, and this problem even increases with these nanotechnologies and nano coatings and nano everything, which actually make recycling even harder job. And unfortunately, we cannot substitute non-renewable minerals with renewable ones. And even green technologies we are a lot of talking about in the last decade need significant portion of non-renewable resources. So like it or not, mining will still be the crucial part of our societies also in the future. So if it's not grown, it must be mined. And I would like to describe you also about this paradigm about the depletion of the resources. The resources will never be depleted. The only question here is how expensive are they going to be? The problem is that this easy access, high grade ore deposits in globally have already been mined out. And now the mining industry strategy to cope with this problem is to go big. So in this graph we can see, made from these two graphs were made during the IVAMOS project, that the average grade is decreasing, or average grade of ores which are extracting today is decreasing. And the mining industry is coping this by going big. So big machines, big open pits, big extraction, large production. But obviously, this won't go in infinity. So mining in the future will certainly need to go in different way. And whether the mining, some certain deposit is economical or not, it's interplay of various factors, a lot of them. So, and if we use the machines and robots in the mine, we can influence to a lot of such factors, which actually differentiate whether the deposit is exploitable, economically exploitable or not. I was mentioned the paradigm change. So what if we, instead of going big and really big, we change the strategy and in going small? For example, in today's mining industry, we will extract the mountain, crush it to the small particles, extract the mineral deposit, and in this way make a huge amount of waste and some unnecessary environmental impacts and so on. If we are able to go small and, for example, precisely mine such kind of deposits or veins and extract only these things which are needed, we could solve a lot of problems. And in this way, many deposits can become economically interesting again. And including these deposits where humans cannot go today, like ocean floor, ultra deep deposits, active hydrothermal vents, or even extraterrestrial bodies, for example. And also the mining is not really suitable area for humans. It's not human friendly. It's hot, dusty, dangerous, and so on. So I will repeat the Agent Smith clause that never send a human to do the machine's job, and mining is certainly the job for the machines. So the vision of the mine of the future, yes, it's like this, that the mining will be completely automated. No humans will be needed underground. Humans will only need to interfere, maybe just give some general guidance or so on. So mining machines can do the job by themselves, are able to distinguish between ore and waste, are able to sense the environment, are able to make their own decisions. Minerals are extracted precisely, less waste is generated, and also mine layouts will be adopted to these new strategies, and so on. So in this picture, yeah, we can see some autonomous mining machines. Downstream industries like ore separation or metallurgical activities are now fully automated, and only metal or end product is transported back to Earth. But there are, of course, many technological challenges. I will mention some of them. Energy supply is a big challenge. So whether we use batteries, or we burn some fuels, or we use hydraulic system, compressed air, explosives, etc., or maybe use some future sources of energy, like nuclear, fuel cells, or fusion. Locomotion. Will these future mining machines use legs or wheels or some other type of locomotion? We don't know. But certainly they will need to move in all three directions. They will need to climb, descend, down. No, certainly will not go only left and right and forward, backwards. And they will need to be surface independent. So in mines, we have everything from very soft substrate like mud to the very hard surfaces like gravel, big boulders, rocks. Rocks, unfortunately, absorb electromagnetic waves, so communication here can be a problem. So how do we solve this issue? So by moving cables around, or by having some wireless repetitors? Will it straight corridors then? There are cutting of hard rocks and productivity, which is very important factor in mining. So if we go for smaller machines, how do we assure back force? This is valid. Today's mining machines are really large, but if we go small, then we need a way somehow to dig to the rock. Are these machines going to anchor themselves? If they are mining under the water, we have a buoyancy effect. So this problem even increases. Also, by crushing the rocks, these small peaks get worn, so they must be replaced regularly. So how are we going to replace them, for example, on the ocean floor? And transportation of ore, so how are we going to transport this to the processing plant? So these are really some local challenges. Data. So these robots will certainly be equipped with some sort of sensors, but we will need some sort of data storage and very powerful processors to process this data, to remove noise, to extract information, to make machines able to decide on their own. So decision support system, artificial intelligence feature. At the beginning, it's also human-machine interaction will be a big issue. So are we going to produce virtual reality, or how are we going to integrate various data into a single system? How these systems can support people at their decisions or whatever. So big data problems. Robustness and resistance to corrosion. So in mining environments, many things can happen, including rockfalls, presence of corrosive substances, radioactive, high temperatures, impacts, magnetic and other fields, everything. So these machines will certainly need to be machines for the future mining. We certainly need to be very robust and modular. In mines, there are a lot of different tasks, but they will also need to be equipped with sensors. They will need somehow to sense their environment, to distinguish ore between the waste and many other things, to be able to make a decision. So inSITE projects jumps here. So within inSITE project, we are really producing new types of sensors which can be used in mining machines of the future. Right now, many changes are happening, mainly in the sense that the people are removed from the most dangerous part of the mine, which is production phase, so where the extraction begins. And here are some systems already developed, which integrate data from many sensors to inside one virtual reality system, and support people operator to operate these machines. Also, some other commercial steps, from automation of different tasks like drilling or cutting rocks or sensing, logging the boreholes and various other things. But these machines are still not autonomous. They are mostly equipped with sensors and remotely controlled. Mining of the seafloor. It's sadly this project, we see these mining machines goes bankrupt, so this never happens. But still, we think that the seafloor will be next step of extracting minerals. Or here, these various dredging systems are shown here. There are also various international projects, research projects. Here, I'm sure you're familiar with UNEXMIN, where INESCTEC is the main technology developer. RoboMiners, Vamos, Badger, AutoFlame, many. These are drones equipped with scanners flying in mines. Badger for automatic boreholes, and so on. And many others. So how these LIBS can be used for the mines of the future? So there have been experts before me who were explaining about LIBS, and I will not explain much about this. But we in this project we were our job was to bring the minerals, to bring the materials that the LIBS experts will be able to calibrate their instrument and to see if these instruments are really good and able to distinguish between waste and minerals and different kinds of materials. So monomineral samples have been prepared and some composite samples of ore and waste rocks, and there are still some other materials which will need to be prepared. So we organized scanning electron microscope and EDS analysis of these materials so that we know somehow how is their composition. There's some fused laser ablation combined with mass spectroscopy and X-ray fluorescence to detect the presence of main and trace elements. And in future, these materials will be measured by the LIBS, by the LIBS spectra, to be able to calibrate our new machines. But this is not very easy task. If you look this example of galena, on the first look, at the first sight, it looks very homogeneous. But if we really zoom in here, we see that it's far from being homogeneous. I have put here the size of the 100 micron laser beam, and it really is important of where to fire it, because you can get really big variation of flat, and also big variation of sink here. And other people already before me already addressed this problem of representativeness and how to assure that your measurements really represent the whole sample here. It's quite a big science behind of that. Here's another example of one very rich pyrite ore. It looks massive, but you can see, according to the EDS measurements, of how big variations can be when you measure with 100 micron laser, when you fire 100 micron laser on different areas of these rocks. So representativeness of the measurement is a really big issue. Then because there are many impurities in rocks, even microscopic ones, you cannot detect with your eyes. Then what do you measure? You are only scratching the surface. Are you measuring dust or dirt or some other materials which supposed not to be there? You never know. Maybe if you measure in some liquid phase, does it interfere with your spectra? What if you have in mines you have a lot of mud? What is if you have opaque medium? Yeah, so spot versus area detection, and what size of the laser are you going to use, and how do you interpret the spectra? I will not go into the details here, so I will conclude with my presentation. But it's the answers here are not straightforward, and there are many challenges ahead in data interpretation in LIBS. So thank you for your attention. And I hope it was interesting for you.
So thank you, Gorat. So some question for Gorat, very fast because we are already completely out of schedule.
Okay.
So just a very simple question. So you show us that the complexity, but we have been discussing that in some instances there are some problems in the mines that are easy to, so there are easy problems for the LIBS. So for instance, a go or no-go decision or a threshold.
Excuse me, I didn't understand you very well.
So you show us there is a lot of complexity in the minerals, but we also have been discussing that for some operational in the mines, sometimes a decision, there are also simple cases. So where a decision where the LIBS can help. You have comment on that?
Yes, every mine is different. There is no two same mineral deposits, and some mineral deposits, we are calling them monomineral. They have very one kind of mineral and one kind of element. Some are polymer. This could be quite easy, in my opinion, to distinguish with LIBS. But other deposits are polymineral, polymetallic, where they have huge varieties of different minerals, different elements. And this part will be a bit tricky, in my opinion. And if we be able to solve these issues, then it will be really good.
Okay, thank you.
Thank you.
Our next speaker is a man of the home, is Alfred Martinez. This is one of the principal researchers of the Center of Robotics and Autonomous Systems from INESCTEC, and also teach in the School of Engineering of Porto Polytechnical. And they have a long experience to develop robots. In this case, long experience to develop robots for underwater scenarios. In this case, and I suppose to go to talk about that in the presentations.
Well, I will try to be brief. This time I will not talk about LIBS or laser, and although I have the word spectroscopy in one of my slides, but I will make a brief passage on some of the on underwater robotic systems that have been used in general, and some of our experience and some of our vision towards the use of underwater autonomous systems in the context of raw materials, mining, and in general in this general application area that obviously, like Gora says earlier, it has a lot of potential. So if we think about what is autonomous or what is underwater robotic systems, they vary from small systems this size to robots the size of the Nautilus machines with 100 tons of weight and with a huge diversity of configurations, propulsion, and objectives. And all of these systems basically do one thing: allow us to go where man cannot go, or it is very difficult to have human activity there. So basically, they tend to be used in two main tasks. One is data collection, the other is intervention. Obviously, the latest one, the intervention part, means that if you want to operate at the sea bottom at 2,000 meters depth, you cannot get a diver there. So basically, the only solution for us to act or to install or to build an infrastructure, for instance, in oil production or mining, is to have a machine there. So we get a robotic system, a system that somehow has some kind of automation in the process. That doesn't mean that we cannot have a human in the loop with teleoperation, for instance, using cables, but the access to these remote and harsh environments always require us to have a surrogate machine that does this for us. So in the context of robotic tools in underwater mining, in scenarios where we think that we want to do raw material extraction below water, there are basically two areas. One of them is the other one that I have not shown yet, which is at sea, and another one is, like we've seen here some glimpse before, is to use robotic tools in the context of mining or raw material extraction inland, obviously in places where we've got water. So basically, either for the exploration of underground flooded mines, I will talk a little bit, I'll show a little movie, or open pit underwater mining that Pedro has talked initially about, for instance, the context of the VAMOS project. At sea, when we look at the usage of robots at sea, they basically are used for surveying, so to collect data about the environment where we want or may want to extract minerals. We can use it in different aspects of surveying, even for large area scaling or for localized data collection, for environmental monitoring, to do the support of operations, to act, and to exploit. So to have machines that in fact do the extraction that we need or harvest the minerals that we want. So basically, there is a trend that passes from data collection towards intervention, which is harder to do, and that also starts to apply these systems in more simple environments or more benign environments, and then try to go to harsher environments, being those either harsher environments in land or deeper waters. If you look at the type of systems that are used in surveying tasks, they are basically autonomous underwater vehicles. So typically torpedo-shaped AUVs like the Thetis robot that you see over there, or the Hugin robot, or gliders, systems that are capable of, at sea, doing missions with a very long spatial coverage and take a wide range of data. This data can be data direct measurements, or like, for instance, acoustic measurements of the sediments, of the density of sediments, or bathymetry profiles, but obviously, typically, they don't take samples back. In terms of environmental monitoring, the same type of vehicles are used. So basically, here, and it is a relevant part, is we need to know what is the impact of our action underwater. This is the impact on the ecosystem. That means tracking mammals, tracking the effects on the water column, the plume, the noise, the nutrients, all the pollution that eventually can happen. So for these kind of systems are the systems of where we got autonomous robots that can sweep an area and measure in the water column the variables that are relevant for the tasks in mission. Like I said before, if you want to go to the sea bottom, especially at deep sea, then you need something like working class ROV, which means, for instance, this is the Portuguese deep sea ROV, the Luso. You need something that is able to have arms and to actuate there, to install a pipe, to install a system, to collect a sample. Obviously, these systems have one big problem. They are big, they are expensive, and they demand a very high logistic support from the surface. When we think about exploitation, basically, we have three main exploitation areas. One is the one that has already been done. We can see in the first picture on the top, which is dredging or shallow water dredging, for instance, diamond collecting near the coasts of South Africa, where you at lower depths, you collect minerals, pick up and dredge the sea bottom. The other is the use of collection of polymetallic nodules. Currently, there is a huge interest from many countries and many private companies to collect polymetallic nodules on the sea bottom. Obviously, there is another possibility, that is to have mining machines like Garaz shown you before. This is the case of Nautilus that now unfortunately has been bankrupt, but these are machines that are aimed at mine the sea bottom. In this particular case, near volcanic hydrothermal vents or former hydrothermal vents. Here there is a huge social backslash with concerns of possible environmental impact. So this is also one of the reasons why, if I would say what would be the next step that we are going to see in terms of use of robotics for deep sea mining, we are talking about harvesting, collecting nodule mines, because it's an easier task. We will need to have a machine that picks up small polymetallic nodules and brings this to the surface somehow. But we have less impact, and it's easier to accept in terms of social challenges. Considering the challenges that are pointed from our point of view, for me that I'm that work on the point of view of the development of the robots, there are a lot of challenges. You can see here, in example of the Vamos case, the mining head of the machine underwater. You can see that from the perception point of view, this challenge, Goraz was already talking about many of these challenges. From the perception point of view, this is really hard for a machine, for this machine in the future to look at the environment and decide what to do, or where to go, or what to mine. This is something that is really tricky on the point of sensors, and this is one of the reasons why we are involved in the inSITE, and we try to push forward to have these technologies. For us, in terms of development of underwater robots, basically this stems for one obvious reason. Portugal is a country of sea, so we have a huge sea environment. We have interests in the sea. Our sea is big, deep, sometimes it's dangerous because we are responsible for the search and rescue in almost half of the North Atlantic. So here robotics is an important tool, not only in the context of mining, but in the context of having human presence on the sea. So this means that, like I said before, we can have underwater robots. It can even be the same type of underwater robots that operate inland or at sea. I will briefly show you two examples, direct examples that have already been referred here, and then I will talk about some of our approach towards long-term permanence at the deep sea. So one of them is underground flooded mine exploration. You are seeing here the UNEXUP UX1 Neo robots. So in this case, this problem is that there is a lot of gallery and underground flooded mines in Europe, and these flooded mines have a lot of requirements in terms of exploration. This exploration can be either because we don't know the state of the mine and we simply are concerned about the stability of the mine, or because we mainly want to know if there is some mineral resources that could be tapped and to be explored further on. Some of those mines have been closed 200 years ago, so they were abandoned at a time where the concentration of ore was deemed to be non-economically satisfactory. Today, like Goraz has shown, the concentration of ore is continuously decreasing. So maybe nowadays we have a mine that has been abandoned 200 years ago that if it was open today, it would be interesting to explore. But to know that, if we want to go there, we need to take out the water, which is an expensive problem. So if we have a robot that could give us some clue of if it takes some advantage to do that, then robots here can help. So this is the case of the UNEXMIN project. This is a project that aimed to develop a robot that could explore flooded underground mines. So this is these mines, as you can see here, they are characterized for the robotics part to be very challenging environments. You combine not only the need to have a robot that goes underwater, that resists the water and the pressure and has the sensing problems of the pressure, but you have to have a robot that is capable of navigating a very tight, constrained space, and you can see here the robot. So the approach taken was to develop small spherical shaped robot with onboard computing, obviously, and a set of sensors that were basically imaging sensors, laser scanning sensors, and a payload of dedicated sensors to gather information about the mineralogical content of the mine. You can see here some data taken from a mine in the UK, from Acton mine, using the laser sensors where the robot is moving down the shaft and it's getting a very precise measurements of the morphology of the wall. We're using laser scanning underwater, it was also developed a structural laser light system that was developed for this task. Following the success of the UNEXMIN project, so basically it ended in a company, in a spin-off company, and it was followed by a scale-up project funded by EIT Raw Materials that take it further, the concept, the robot, from a prototype with a lot of problems of operating in the field. So in order to have a prototype or a robot that could be easily used by other operators and that would have more capabilities in terms of not only operational conditions, but also in terms of mobility and the type of information that could bring. So this is the same thing, the idea is the same. We want to get a sphere, like a ball that you can drop in your shaft and it would explore. Obviously, you are seeing that it has, you can see here on the top, a small fiber optical cable. And this is because independently if the robot is moving autonomously or not, we want to be sure, at least at this stage of technology, that we control the process of development. We are still needed at least to tell the robot, measure directions. Shall I go to the left? Shall I go to the right? Should you explore this shaft? Should I explore the other gallery? And obviously to solve some problems where the robot cannot decide. So this is a really hard environment. These images were taken in Molnar János cave in Budapest. And you can see here that in this point, there are points where we say the robot explore 100 meters of shaft and then give me the control. I will guide it to this path and then I will go down to a certain place. When we think about open pit mines exploitation, we see an image of Limur mine in the VAMOS demonstration. One example of this is, like I said, like it was said before, the VAMOS project. So here, the idea is that there are a lot of open pit mines and that most of them have water. So typically the process of mining involves taking out the water and simply digging around. This has two major problems. I take out the water, I've created an environmental problem, and I will pay for that, also in terms of costs for operation. And also, I will need to dig a bigger hole as I go down. As I go down in vertical ore bodies, I will start, because I need to have places to put the trucks and to move around it, so I will start to excavate a bigger and bigger and bigger hole, which also has a lot of impacts. So if we could put a robot underwater the sea, like you see here, like Pedro shown before, and if I can operate it down, I could excavate without taking the water. And this is the idea was the idea of VAMOS project. So in the VAMOS project, you have a surface support barge that is seen here, a hose that transports the mineral that is mined from the bottom, a mining machine, so it's an underwater excavator, a robotic underwater excavator that is dropped in the bottom, and then it moves, it is controlled by the surface, so energy is provided by the surface because it must need always to be connected. Most of the solutions that are nowadays considered, for instance, for operation at sea, either being it polymetallic nodule collection or direct mining, direct rock cutting, always include the provision that the machine is on the sea bottom and has a riser up to a surface ship that controls. In this case, the surface ship is a standard platform that is put in the middle of the pit lake. And like I've seen before, this system has a 3D environment, virtual environment that gathers information that comes from sensors on the machine, but also from sensors from additional robots. One of those is the EVA AUV, which is a robot developed to gather precise information of the 3D morphology of the underground, under the water part in continuously. You can see here the results of the data continuously provided by the AUV of the bottom of the lake. When we think that we need to go to the deep sea, obviously, I can always say that I will pick up a solution like the VAMOS one. I will have a ship at the surface, a mining machine at 2,000 or at 6,000 meters of depth. And then I will have a link, electrical link, and a riser where I pump up the sludge, and the slurry, and I will mine the floor. Typically, for this, I need to solve some problems. And some of the problems are, how do I locate elements on the bottom? Because it can be up to 4 kilometers, 6 kilometers of distance between the boat and the mining machine on the bottom. So for that, we have been addressing the possibility of putting robots on the sea bottom in a semi-permanent basis, which is the turtle lander concept, which is that a lander that is a robot. So I will drop the landers on the area of operations and they will stay there. There, they will form like a GPS satellite constellation, but instead of using radio, they use acoustics and this allows us to localize other elements, either mining machines, other robot tools, other elements that you want to put at the bottom of the sea. If you move to another area, the robots are capable of redeploying themselves to another position. So typically, we already have 3 generations of those. This is the generation 2. This is some images from tests that we made with 2 of them in a coordination motion in an exercise in 2019, before the pandemic situation. And currently, in the 3rd generation, we already have deployed in this summer in the context of the NATO REPMUS exercises. For that, I would like to show you our most recent acquisition, which is not a robot, is a research ship, a technology development ship. So that is a tool that allows us to deploy these kind of systems in a relatively cost-effective way. You must notice that when we are talking about the other big machines, we are talking about systems that can have boats with over 70 meters long of hull length, and this is a boat that allows us to go to the sea and access, in the case of the northern on the Portuguese shore, to access deep sea areas and to operate there. So where are we heading? Us, as INESCTEC and INESCTEC Robotics, but also the community in general and the robotics community in terms of underwater community. So we are obviously heading towards automation. Automation in the big sense that the integration of new technologies from the perception point of view and the processing of the data, integration of AI, the availability of high quantity of data. Obviously, also, there is a growing trend from getting higher efficient and higher operational systems, in particular when you consider autonomous underwater robots. If you look at the history of autonomous underwater robots, you look that they pass it to be big robots that needed a huge crane, that had a very specialized set of people that to operate, to smaller vehicles capable of doing almost the same type of operations, in particular in data gathering, and to access the same environment or the same depth with lower costs. Obviously, some of the limitations in terms of types of sensors or payload that you have in these systems can be overcome by using multiple systems and have some coordination, using the system as a set of robots as a global system that interoperates and communicates by itself. And obviously, there is always this aim to get longer times at sea, longer autonomy, stay more time with more reliability. This comes from needs of operational costs, improving efficiency, but also to have higher reliability. And obviously, new sensors, typically, and this is one of the reasons, like I've said before, where we think that the inSITE can provide us some new pushes, is to start to adapt to the deep sea or start to use technology that is already used in other contexts, but now use it underwater. And, for instance, in this case, the word spectroscopy in bold. So these are the global trends, and I hope that you get somehow a glimpse of the usage of robotic tools for underwater, mainly in the context of raw materials. And I would like to thank you all for your attention. I hope it was short enough.
Thank you, Alfred. If you don't mind, we will skip questions because tomorrow we will have the chance to see some of these machines in real time on the guided tour to the lab. And now we will finish with another perspective. So we have been in the mines and in the ocean, and now we will go out of the planet. And for this, we take invite Slavka Carvalho. So she's coming from Slovakia. She has a very diverse career. She was in the United States, Maryland University. She's a chemist, Maryland University, and have the chance to work in many projects with NASA. And she's now, thanks to Trump, she's now an asset to Portuguese science. She's working in Aveiro, and she still maintains strong connections to NASA Astrobiology Laboratory, and she will give us a perspective on these applications. So please.
First of all, thanks to Anna Pires and organizers for having me here. And it's my pleasure to share with you some exciting science which Curiosity Rover does on Mars. And especially because this talk is not about LIBS or robotics, so I hope that you will forgive me. So, before I start, actually some science, I think it is important to mention the non-disclosure agreement because when you start to work at NASA, of course, that you need to sign this confidentiality agreement, which practically means that 5 years after you finish your contract, you are not allowed to talk about the details of your work or your colleagues' work unless it is published in form of papers. Anyway, I think that I'm going to show you pretty exciting stuff, so we will see. Okay, so let's go back to Curiosity Rover. Curiosity Rover landed on Mars. Okay. It doesn't work. Okay. August 6, 2012, in Gale crater, with the main scientific goals, like to study habitability of the Gale crater and to search for environments favorable for past or present life. So for that, the Curiosity Rover is analyzing geology and geochemistry, analyzing role of water, presence of organic molecules, and is studying radiations at the surface on Mars. So Curiosity Rover, for that, is like traversing this Mount Sharp mountain and is studying these different geological units. So some facts about the Curiosity Rover. So the mission name is actually Mars Science Laboratory. Why it is Mars Science Laboratory? Because it is actually really science laboratory. Many people think that it is just some vehicle with 6 wheels, which is making cool pictures of Mars and some cool selfies, but no, it makes really, really nice science. Rover name is Curiosity, and it is also she, it is a girl. So size, it is pretty big a rover. It has size of like big car or SUV. It has also arm, where is the laser, which can reach about 2 meters. It's pretty big. It weighs around 900 kilograms. It's also pretty heavy. So as I told, it is geology lab. It has a rock vaporizing laser and a lot of cameras. So the mission, as I mentioned before, was and is to search areas of Mars for past or present conditions favorable for life. It launched on Mars in November 2011 and landed there in August 2012. So it was in space, actually. It takes 9 months to travel from Earth to the Mars. And length on the mission was, at the beginning, 2 years, 2 Earth years. But as you can see, the rover is there making cool science even now when we are in 2021. So it is pretty impressive. So here are some instruments of the Curiosity rover. So rover has 10 scientific instruments. It has 17 cameras. That's why he makes those amazing pictures. And he has the laser, which is here, which you are super interested here in this workshop, right? It is, the instrument is called HemCam. It contains LIBS, and it will be tomorrow Amy McAdam, which is actually my NASA supervisor, and she will tell you much more about this instrument. So this is the laser, and it has also the drill here, which collects the rock samples. So as the Curiosity rover traverses on Mars, on the Gale crater, it is drilling the samples, as you can see here. Until today, we have approximately 30 samples, and you can see they have different colors, and the Curiosity rover drove 7 kilometers. I cannot forget to mention, it is important that the drill collects sample in the depth of 5 centimeters, okay? And also, this is just for curiosity, this is a mineralogical composition of several Martian samples. And here I want to mention that these green parts of the circles are clays. And as I'm going to talk about clays, I want you to remember that I was already mentioning that. So to analyze actually those drill samples, Curiosity rover contains 2 very important instruments. So one is called HEMIN. It is here in the heart of Curiosity rover, inSITE. It is chemistry and laboratory instrument, and it is X-ray diffraction instrument, and it measures the crystalline mineral phases in the Martian regolith, right? And the outcome, of course, is the XRD diffractogram of different crystalline phases. And again, as I am not a rocket scientist, I am the one who actually analyzes the data from the rover. I have here video which will explain you exactly how these things work. And now I don't know if I will do the good job. Oh, thank you.
When NASA's Mars Science Laboratory lands in a region known as Gale Crater in August of 2012, it will be poised to carry out the most sophisticated chemical analysis of the Martian surface to date. The minerals on Mars may reveal a chemical record of past and present environments, but the right tools are required to read this record. One of the 10 instruments on board the rover Curiosity will be CHEMIN, short for Chemistry and Mineralogy. Developed by Ames researcher David Blake and his team, it will use new technology to analyze and identify minerals in the Martian rocks and soil.
The measurement we're making is called powder X-ray diffraction, and it requires a powdered material, and quite often it's very difficult or impossible to powder a material finely enough to get a good pattern. We developed a method for shaking the grains at sonic frequencies that allows the grains to actually flow like a liquid through the beam. And when this is done, then all the crystals, as they go through the beam in random orientations, even though they're coarse-grained, have the appearance to the beam of being a fine-grained powder.
An X-ray beam no larger than a human hair will fire into the sample, causing the beam to scatter and also fluoresce the sample particles. A CCD sensor will capture the information so that it can be relayed to scientists back on Earth.
For planetary exploration, rather than trying to get a sample and bring it back to Earth, which is a very expensive and complicated procedure, we can now do laboratory quality analyses on the planet's surface in real time.
Different minerals are linked to certain kinds of environments. For example, some form with lava, some form with water. Scientists will use CHEMIN to search for mineral clues indicative of a past Martian environment that might have supported life. What makes it possible for Curiosity to carry this CHEMIN instrument is over 20 years of development by David Blake and his team. A device that once was the size of a double refrigerator has now been reduced to about the size of a briefcase. Variations of the instruments have been adapted for field work in geology, transportation security, and analysis of art and antiquities.
So another instrument, very important one, to analyze again drill samples is called SAM. SAM is a sample analysis on Mars instrument. It is made up of 3 different instruments. It is QMS, TLS, and GCMS. And this instrument was actually specifically designed to analyze organic molecules on Mars. It is also here situated in the belly of the Curiosity rover. And until today, it is actually the most complex instrument ever sent to Martian surface. So how this instrument actually works? So, and I forgot to tell that the size of the SAM instrument is something like a microwave oven. So not that big and also not very small. So in the SAM instrument, you hit the sample at around 860 C, and the outcome of this instrument are the masses of evolved gases. Okay, so mass of hydrogen is mass 2, mass of water is mass 18, etc. And again, I have here another cool short video. Okay.
We want to know, has life ever existed on Mars? Do pockets of life persist on Mars today? NASA's approach to answering these questions is to break them down into smaller and smaller steps. First, we need to know if ancient Mars was habitable. Did it once have the right climate and the right chemistry to support life? The Curiosity rover is investigating these questions by looking for organic molecules containing carbon. Organic molecules are the backbone of all life on Earth, though they can also come from non-living sources. Today, the surface of Mars readily destroys organics, making them difficult to detect.
We are decelerating.
6 years ago, Curiosity landed in Gale Crater on an ancient lake bed. A few months after arrival, it drilled into sedimentary rocks and detected traces of organic molecules using an instrument called SAM. Now Curiosity is climbing the mound in the middle of Gale Crater, and SAM has made a subsequent detection of organics. This new detection is exciting because it comes from rocks that are billions of years old. That means that the organic material within them is extremely ancient. Some of the organics that SAM has detected contain sulfur, likely introduced through geological processes. Sulfur can act as a preservative, binding organic molecules together to make them tougher and protecting them from oxidation. In fact, sulfur is the element that makes hair and fingernails tough, as well as vulcanized rubber. Martian sulfur has probably had a similar effect on these old organic molecules, helping to preserve them over geological timescales. SAM made the new detections by heating samples of crushed rock to very high temperatures, above 1,000 degrees Fahrenheit. This vaporized the samples and released several species of small hydrocarbons like benzene and propane. Because the hydrocarbons were released at such high temperatures, they may be the fragments of bigger, heavier molecules within the rock similar to kerogens. On Earth, kerogens are found in rocks like black shale and coal and are the products of ancient plant and bacteria. We don't know if the recently discovered organics on Mars are of biological origin, but it's exciting to find such old material preserved right at the surface. This finding is also encouraging for future exploration. NASA and the European Space Agency are preparing to send the next generation of rovers to Mars in 2020, carrying new technologies to search for signs of microbial life. In the distant past, Mars was much warmer and wetter than it is today. The rocks at Gale Crater tell us it was once an environment where life as we know it could have survived. The discovery of ancient organic molecules shows that another ingredient of life was present at that time, and it broadens our understanding of habitability of both ancient and modern Mars.
Okay, so as Jen Eigenbrode, actually now I will mention, so she had office next to me when I was working at NASA, and I was there when she was talking to this TV, so I feel like personal connection to that video when I found it out on the internet. It was really, really nice. So as Jen Eigenbrode already mentioned, the SAM is really spectacular instrument. In 2014, organics were confirmed first time on Mars by SAM. So in 2014, as was told by her, so we discovered chloro-bearing hydrocarbons. Then in 2018, we discovered sulfur-bearing ones, and this is very new. The SAM discovered long-chained hydrocarbons. So it is very, very interesting because all these organic molecules which were found on Mars are in strong correlation with the clay minerals there. And also, this is also really spectacular discovery because not many scientists believed that there will be organics on Mars actually preserved in those 5 centimeters of Martian regolith because We know that Martian surface is pretty dry. It is very, very irradiated, and Mars doesn't have any atmosphere. So we were thinking everything is destroyed if it is there. And no, we have still something there. It is really, really, really impressive. So there was also a NASA press release in May this year related to the topic that salts could be important piece of Martian organic puzzle NASA scientists find. And this is related to this paper, where I appear to be co-author. And in this paper, we are mentioning that on Mars, we detected acetates and oxalates. And why they are so interesting actually there? Because on Earth, we have organisms which can use acetates and oxalates for their energy. So can be acetates and oxalates source of energy on Mars by something living there? We don't know. Okay, so we have organic molecules, which we detected on Mars, but we do not know where they are from. So the sources can be two, or it is endogenous sources, like they could be synthesized in the atmosphere, is from hydrothermal activity or biosynthesis, or it is exogenous source, where the organic molecules were brought to the surface on Mars by meteorites or comets, etc. So also this is a question we do not know the answer yet. So again, we have organics, we still do not know where they are from, and we still do not know what is the, I call it mother molecule. Why I'm saying mother molecule? Because you remember these decane and dodecane from previous slides. So these organic molecules, which actually some detect, are the products of thermal decomposition of something bigger, right? So one of the possible sources of these alkanes are fatty acids, right? If you see the structure of fatty acid, and when you heat it, you remove this COOH group. And then you have alkanes, like decane or dodecane. And why are fatty acids so interesting for us? Because on Earth, they are primary constituents of terrestrial cellular membranes. And of course, fatty acids are precursors of lipids on Earth, which is pretty impressive. Okay, so let's go back to Earth. So this is my favorite slide because it is related to clays. So it is believed, there are some theories that actually life on Earth arose in the clays. And why is that? So clay minerals, this is actually the structure of clay minerals. It contains tetrahedral sheet or silica tetrahedral sheet combined with alumina octahedrons and again attached to the silica tetrahedrons. So this structure has high specific surface area and it has this optimal interlayer space where organic molecules could be concentrated, they could react with each other, and they could be actually even protected from the harsh environments, right? Because they are hidden in the middle of these two units of the clay mineral. So this is really cool. Also, we know that meteorites contain organic matter like fatty acids, amino acids, or nucleobases, right? And they were confirmed in the strong association with clay minerals. So we also know that clay minerals are on Mars. You remember those circles and red parts? So we know that they are there. And so here comes the big question. Could be the amino acids, fatty acids, nucleotides, etc., present by clays on Mars? And this is actually work which I was doing at NASA, and I'm still continuing doing here in Aveiro. So to reply to this question, we need to prepare organoclays, or mother molecule clays, which we call Mars analog. And why we need to prepare? Not because we do not have Martian samples here on Earth, unfortunately. So we need to prepare something, what we think that we found on Mars, and then we need to compare data which we acquire on Earth with those acquired by Curiosity rover. So, clays. So I usually work with clay which we'll call non-tronite. You can see the color. It is like color of the Mars, right? Because it is iron-rich material or mineral. And then non-tronite is a standard mineral, actually, which we are using, which many universities and laboratories use. We use the same one. It is from Australia. It is called NaU2. And then I chose here the most primitive amino acid, which is glycine. I was working with much more many amino acids, but just for demonstration, okay? So what I do, I combine this non-tronide with glycine, and then I synthesize the organoclay where glycine is here in the interlayer space of non-tronide. And when we have this done, we need to run EGA analysis, which is SAM-like analysis on Mars, or INSITE analysis, which is chemical-like analysis on Mars, okay? So this is laboratory at NASA. So as I was saying, it is SAM-like or chemi-like instruments. So we have actually twins of Curiosity rover instruments in our laboratory. So this is actually SAM or EGA. We had 3 different instruments. Here is one, here is again the same one, and the third one is not mentioned here. And this is Chemin-like instrument. You remember the video, which was David Blake showing? So we have the same instrument, which is actually here. And I spent a long time in this chair because I was working with this Terra instrument. And I need to also remind you that operational setup of these instruments, EGA or SAM-like, or Terra, INSITE, or Chemin-like are the same as those on the Curiosity rover. So what we do there, we can really compare with the data on Mars. So, and this is really cool instrument because my NASA boss, Amy, took this instrument to Antarctica, Australia, Hawaii, Iceland, and it is really, really, really nice because you can go somewhere and you have the data in situ in the same day, and it is really, really amazing. And here is an experiment which I will talk to you about later. So even at NASA, I have to improvise sometimes to do some experiments. So as you can see, it is not super high scientific as you can imagine. Okay, so when I prepare these Mars analogs, as I mentioned before, we run them in Chemin-like or SAM-like instruments. So this is EGA SAM-like analysis. When I was mentioning that the outcome is are masses of evolved gases, right? So if you heat organic sample, you are always super interested in the evolution of CO2. So what we did, we ran the sample, and the red stuff is mass 44, which is actually CO2. And then we, of course, compare the data with the Martian samples. But if you can see this sample, which is Mojave on Mars, and the temperature evolution of my sample, which is around 380 C, it is pretty similar, right? So we were very, very excited with this data because one sample is really, really similar than ours. So in theory, we could say that there is possible glycine in the clay samples which we analyze, right? But, of course, on Mars, nothing is that easy. So this is mass spectrum of glycine. What does it mean? That I was showing you mass 44, which is CO2. But glycine has all of these masses. It means that when you hit the sample, you need to get mass 16, 17, 18, 27, 28, 29, etc. So what I did with mass 44, I need to do with all these masses, and we cannot forget that. Mass 30 here is 100%. For example, mass 44 is 5%? No, I don't know. Yeah, see, 5%. So also, evolution, when you see the EGA data, so your mass 30 should be 100%, and your mass 44 should be those 5%. And if it is not, you need to subtract many, many data from other data, because we also know that your sample is not monomineral. It might contain different organic molecules. And not even mentioning that mass 30 is, for example, NO, and NO is also evolution from nitrates as NO. So NO has also different composition of mass spectrum. So we need to also subtract data from different minerals from, it is really, 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 really complicated. So just for you to see, I showed you one slide, but behind this slide is hidden months and months of hard work because it's really complicated. Right? So, and this is again comparison of my sample with Chemin-like instrument, right? XRD1. So this I ran in like normal-like conditions because on Earth it is actually super easy to distinguish different clay minerals from each other. And we do it based on the position of this peak, of these peaks, which are actually these spacings, or D001 spacings. So it is actually this unit, so it gives you information how, like, what is the width of the structural unit of the clay, right? So let's see, this is, green one is non-tronite, just non-tronite without any addition of glycine. It gives me 12 angstroms, okay? When I add it, this is just different kind of work which I was doing. I was adding different amounts of glycine to my sample, and I just wanted to see the differences in these spacings. So again, on Earth, we see that there are differences, which is really cool. But of course, we go to Mars, and on Mars must be everything complicated. Why? Because all the clays on Mars gives us this spacing 10 angstroms. And why is that? Because again, Mars is super dry, and in this spacing, because water evaporated, all the clays got collapsed. So whatever you have inside of the interlayer space, and go back here, will give you 10 angstroms. Doesn't matter if it is organic molecule or inorganic molecule, whatever. So that's why the situation is so complicated. So I did this collapsed experiment when I simulated Martian conditions. I desiccated my samples for 3 hours, and I ran them on these Chemin-like instruments under the nitrogen flow. So what I did, what I got in the end is that under these conditions, only one sample got approximately 10 angstroms, and it is just this non-tronite without any addition of glycine. So all the glycine samples have much higher D-spacing, right? But when you see properly a Martian X-ray pattern of sample marimba, here in X-ray you have like a bit of tail, right? The peak is not completely going down. So in theory, we could say that in this place, there is a bit of tail of this broad band, there could be hiding some clay containing some amino acids. So this was really, really also interesting discovery. And this is my last slide. I was really on time trying to not to prolong the conversation. So, okay, we have organic molecules, but many people ask, what about life? We did not discover life on Mars. We just found clues of that simply life could arise on Mars. I'm sorry that I'm speaking like this, but I'm choosing the correct words because it is complicated. So we know that there was water. We know that Mars had atmosphere. So we found all those chemical elements which are here and confirming life, like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. But also we cannot claim that we found life only because of one thing, and that's because Curiosity rover doesn't contain any life detection instruments. That's why there is another brother or sister now on Mars since February 2021. There landed Perseverance rover, which is this one. And the mission goal of this rover is actually that it is collecting the samples from the Jezero crater. And these samples will one day, we believe around 2030-ish, will be sent back to Earth. And what is good that we finally can analyze sample here from Mars on Earth with all possible instruments we have here. So if we see something, we might confirm, okay, this is life, because we could really see it on microscope or other instruments. And there is ESA, which is ExoMars 2022. This is different rover. And the good thing is that this rover will have a really, really long drill system. The drill will go down to 2 meters. So we believe, even if we found organics in those 5 centimeters of Martian regolith, if there is something, it could be something really down. So let's see, but we need to, of course, wait. First, when will come there some lander, and he will take samples back to the Earth from Mars 2020. And also we need to wait if successfully ExoMars will land on Mars next year. So anyway, Curiosity rover is making really, really nice job, and I really like her. And this is everything from me for today. Thank you very much for your attention.
Okay, and this is it for today. So we will. I hope you enjoy as much as I enjoyed the diversity of topics and technologies that we have seen. So tomorrow we continue at the same time, 2:30. Hope you can join us. So if people that are remotely and are nearby and feel motivated, please, you are welcome to come. There's plenty of space. I think we are relatively safe, I hope. So please keep tracking us, and so keep attention, because in the end, for the students, me and Anna will be sending some inquiries to see if you are paying attention, and to give you the certificate of attendance. And that's it. So thank you very much for your presence, and thank you again, all of you, for participation, and see you tomorrow. Okay. Bye-bye.